This screencast is about carboxylic acids, a class or organic family that involves the carboxyl group, which you can see, the carboxyl functional group, which you can see displayed right here. Alrighty, so having a look at a homologous series of carboxylic acids here on the left, we can use these as an example of how to use the IUPAC naming system for carboxylic acids. They get the suffix oic acid. Alright, so going down this group, we can see that for the first one, the longest carbon chain is 2. Again, you would number it 1, 2, because you would give priority to the carboxyl functional group. The carboxyl functional group is always terminal, it's always on the end, so the carboxyl carbon is always going to be carbon 1. That's just the way it is for every single one of these. 2 carbon compounds get the eth prefix, so this one is going to be called ethanoic acid. Okay, ethanoic acid. This is commonly known as, this is a really common organic compound here, and it's commonly known as acetic acid, but that's not the proper IUPAC name. The proper IUPAC name is ethanoic acid, and it's the acid in vinegar, or if it's really concentrated, it's a really important organic reagent called glacial acetic acid, or concentrated ethanoic. Alright, so we keep on going down the list here. We've got a 3 carbon carboxylic acid. That is going to be called propanoic acid. Propanoic acid. And then if we keep on keeping on down here, we've got the 4 carbon version, which is of course going to be called butanoic acid. So we can look a little bit at some of the physical properties of these, practice naming them. I guess while we have this image on, we'll have a look at the physical property, of course, that we mentioned several times, but as you go down here and the molecules get larger, you're going to have an increased boiling point and an increased melting point because you're getting an increased number of electrons and you're going to get an increased amount of dispersion or London forces between those adjacent particles. Alright, so in terms of physical properties for carboxylic acids, if you look at their structure, you should be able to tell, or to predict, that they do actually have hydrogen bonding capability between adjacent carboxylic acid molecules, and that's because they have an OH bonded together unit there. Okay, and so this means that they can hydrogen bond with each other, and because they can hydrogen bond with each other, that means they have relatively high melting points and high boiling points. Okay, they have lots of forces that, lots of intermolecular force that help keep these compounds together and help them resist changing phase upon input energy. So they can hydrogen bond, and they have relatively high melting point, boiling point. Also, they are water soluble, okay? And that's because, as you probably have also predicted by now, they can hydrogen bond with water, okay? So water, of course, has OH connectivity, and so do these, and so they can hydrogen bond in water. The smaller they are, the more water soluble they will be. So that's also generally a trend with most things that are water soluble. The larger the molecule, get enough space to fit this in, the larger the molecule, the less water soluble. And you may be wondering why that is. Well, it's because in order to be dissolved, or to be what we call solvated in chemistry, they have to be able to be surrounded by water molecules. And as the molecule gets larger and larger and larger, it's tougher. Even if it can make hydrogen bonds, here at the end, it's harder for the thing to get totally surrounded in water molecules. Okay, so just imagine it would have to be completely surrounded, and that's what holds it in solution. And the bigger it is, the harder it is to get surrounded. So we see that most organic molecules are less water soluble the larger their molecular structure. Okay, so a little bit of naming and drawing practice for carboxylic acids. We have first this one here. Draw a 2-ethyl 3-methyl pentanoic acid. By the way, these are dashes, even if my poor cheap stylus doesn't show it very well. So we'd start with the pentanoic. That's 5 in a row with the terminal carboxyl group, of course. And then remember that this automatically becomes carbon 1 because it gets priority housing the functional group. So we want to make sure we fill the thing out with hydrogen and put these alkyl substituents in where they belong. The methyl group belongs on carbon 3. And the ethyl group belongs on carbon 2. Now you may also say, well, hang on a second here. Because why are we writing ethyl before methyl? Remember, this is not based on their number, but it's based on the alphabetical order, right? So ethyl comes before methyl because E comes before M in the alphabet. All right, now fill the rest of it out with hydrogens. And there you go. All right. So then we got to name the one at the bottom here. The one at the bottom has 1, 2, 3, 4 carbons in its longest run, so we know it's going to be a butanoic acid. Then we have some substituents. We have 2 methyl substituents, and they are both on carbon 3. So we do this like this. We say it's a 3. Oh wait. We say it's a 3,3 dimethyl, because there's 2 methyl groups. 3,3 dimethyl, and I should write it all as one word here. Oh, I can. Here we go. Dimethyl butanoic acid. Ta-da!